physical science time. Today we are talking about chemical reactions. Let's put that up here. Chemical reactions. The first thing we're going to do is we're going to address the bell work. And then if there's time after I'll try to go through this pretty fast, and if there's time after that, we might go in the lab and look at some chemical reactions. We'll probably just have time for one or two, but better than nothing. And I might have someone, a good videographer, probably Ethan. Keslin is the one who said that. I might have Keslin. Good morning, Camden. Welcome, Camden, to television. Welcome to television. I said, say hi to the future. Hi, future. Okay, get out of here. We're gonna restart the video. Someone who's a good videographer. We might even film the little demonstrations for the people who. Cool. So we might have someone who's a good videographer film the demonstration if there is one, so that everyone can see it, because there's about 6 people gone, which is fine. That's a very small proportion of you monstrous 9th graders. I almost said 8th graders. Okay, so we're talking today about chemical reactions. Just one thing right off the bat is we sometimes abbreviate this word Rx in or Rx in S. So you should write that down. If you see that on your test, which it will be, know that that word means reaction. It's abbreviation for reaction. Why would we want, this will be the first thing in your actual notes, why would we want to have an abbreviation for this subject? That tells you something about it. What kind of things do we abbreviate? Just for fun? No, things that are long. Okay, it's kind of a long word. That's a good, yes, that's the main thing we abbreviate. Why else would we why this specifically? Yeah?
Just to make it sound like Future Farmers of America ain't that long, but it sounds like
okay.
FFA.
Okay. I think you're right. That is a reason we abbreviate things. That's probably not this one. It doesn't sound better. It sounds worse, I think. But it is shorter, and we use it a lot. Like, we write this word a lot, and so we want to have an abbreviation for it is the other thing. The general form for a chemical reaction is this, and you should just reactants yield products. This arrow here is pronounced yields. Kind of like, if you make a box of brownies or a box of cookies, like if you get mix from the store, on the bottom it'll say, or even in a recipe, if you're fancy, and the recipe it'll say yields 36 cookies or something like that. Yields 3 dozen. Yields means that's how much it produces. So the reactants are on the left side, the products are on the right side. This arrow always points from the reactants to the products, and we pronounce that as yields. So for instance, if we have, in this very simple chemical reaction, if we have HCl plus Zn yields ZnCl2 plus H2, that's how you pronounce it. You can either say the names that you should be able to do now. Hydrogen chloride plus zinc yields zinc chloride plus hydrogen gas. Or you can say the symbols. HCl plus Zn yields ZnCl2 plus H2. Either is fine, but how do we pronounce this? Plus. How do we pronounce this? Yields. Yields. And the rest of them we just say their names. Will.
Where did you get the...
Hold on a second. Same thing, but that was for nuclear reactions. These are chemical reactions. We call it yields. Yes? Great question. That's the next thing we're going to do. Hold on to your horses. Good. Excellent observation, boys. The reason we do this, the reason that we have chemical reactions is that we know they must satisfy this idea that we talked about before called the law of conservation. Please write this down. Conservation of mass. The law of conservation of mass. And this idea was it's been true for the entire history of the universe, but it was maybe not even discovered, but it was coined, the term was coined by, in French, Antoine Lavoisier. Antoine Lavoisier in, I meant to have this, 1787, I think. In 1787, he discovered that in every reaction, tell me what happens. What is true of the law of conservation of mass? Or, yeah. So matter, we could say mass either way. Matter is never created or destroyed in chemical reactions. Matter is never created or destroyed in chemical reactions. Basically, if we had Well, we'll come back to that, but let's say we had just very easily, if we had, and the example the book gives is this, if we had 10 grams of mercury 2 oxide plus, decomposing into 0.7 grams of oxygen gas and 9.3 grams of mercury, these things have to add up. 10 grams has to be the same as 0.7 plus 9.3. That's the example the book is. This was his experiment that we never say prove, but this experiment that provided evidence for the law of conservation of mass was he took this salt of mercury, what he called the calx of mercury, mercury 2 oxide, which was used to treat syphilis, so he had to go buy it from a syphilis treater, and he shined a concentrated beam of sunlight with a magnifying glass on it, and it decomposed into oxygen gas, which he collected in a jar, and mercury metal, which you know what mercury metal looks like, silvery liquid. And so he could tell that this was actually made up of these two things, even though this one was usually invisible, and he could mask this one, even though it was usually invisible. And he found that this much mercury plus this much oxygen yielded the same amount, 0.7 plus 9.3 is the same as 10, right? So when he started with this amount, and that was his real contribution to chemistry, was that people had done chemistry before, but he was an accountant. That was his main job, and so he counted coins. That's what an accountant does. I mean, they're not coins today, but he counted money. And so he was very used to doing this kind of math, and using his day job with his hobby, chemistry, he found the law of conservation of mass, which is kind of interesting. Let's go back to this. What's the matter with this? Why Will and Fate correctly pointed out that there is instantly seems to be a problem with this. What is the problem?
There is another chlorine on there.
Yeah. And we know these have to be here because zinc's charge is always 2+, so it takes 2 chlorines to make it happy. And we know hydrogen is diatomic, so these have to be here. This is right. But this is very clearly violating the law of conservation of mass. This is what we call unbalanced. This is what's sometimes called a skeleton equation. Skeleton equation, which means it's unbalanced. And that's the main thing we're doing this chapter, is we're balancing chemical equations. We'll do that first, and then we will talk about the types of chemical reactions, and then we'll be good to go as long as you have your vocab done. There are a couple things in the last section that we're not going to talk about at all, but they're just vocab words, so mark my words. So this is the skeleton equation. Let's write it as a word equation too. I'm going to write it underneath as a word equation. You don't always have to do this, but I want you to be familiar with word equations. This is hydrogen chloride plus zinc yields zinc chloride plus hydrogen. This is a word equation. Do you see the difference? Yeah, nice. Connor, you're so good at science. This is the word equation, which is made of words, whereas the skeleton equation is symbols, but it's not balanced. And now, let's balance it. So, the first rule of balancing is you don't talk about balance. That's just a joke. That's from Fight Club. The first rule about balancing is you can never change the subscripts. Why not? Last chapter, we were changing the subscripts up and down. We were just like, pew, 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 changing the subscripts. You can't do it here because now we're talking about an actual chemical reaction. Remember, this is not the same thing as this, right? They have the same elements. This one's hydrogen peroxide that if you drink it, you'll die. And this one's water that if you don't drink it, you'll die. You know me?
How come hydrogen peroxide you put on your skin and you can't drink?
You shouldn't put it on your skin. When do you do that?
Hydrogen peroxide, like when you cut.
Yeah, that's no longer recommended, but it is antimicrobial, but there's better things to do. Anyway, so these two things are completely different, and the only thing that's different about them on paper is their subscripts, but these are two totally different substances. So we can't just change what the substance is. We had to do it when we were writing names and formulas because that was the truth and we were trying to find what the truth of its formula was. But in this case, we can't just change the formulas. We can't change this from HCl, which does exist, to HCl2 just to make it happy, which does not exist. So what can we change? Well, we use coefficients. Have you heard of coefficients like in math? Yeah. So kind of think of these as variables. We use coefficients to change it. So if I have 2 chlorines on this side, which you can see I do, right? There are 2 chlorines. The subscript goes just to the chlorine. The subscript goes just to the chlorine. Let me say it again. The subscript goes just to the chlorine. How many chlorines are there? 2. How many zincs? 1, because the subscript goes just for the chlorine. So if I have two chlorines on this side, what can I do over here to make it so I have 2 chlorines? Well, I can put in a coefficient, but that's it. The coefficient distributes across everything. How many hydrogens do I have now? How many chlorines? 2. So I have 2 hydrogens. On this side, how many hydrogens do I have? 2. 2 chlorines. On this side, 2 chlorines. How many zincs? 1. And on this side? So that's balanced. Now we say it is, with this 2 in there, it is balanced. Why would we balance a chemical equation? To satisfy the law of conservation of mass. Because if I start out, if you think about this as real atoms, not just letters on a board, if you think about it as a hydrogen and a chlorine stuck together with a zinc floating around, and it combines to form a zinc with 2 chlorines and 2 hydrogens, well, you see that we have to get more atoms from somewhere, right? If this is a red and a blue Lego and a yellow Lego, and we recombine them like this, we have to get more Legos from someplace. And the answer is we need to double this many. There's only ever one solution for these, okay? So don't worry about getting it. If it's balanced, it's right. We will deal with this more. We're going to talk more about this when we do our worksheets. In fact, that's what your worksheets are about. Like I said, this is the main thing we're doing this chapter, is balancing these chemical equations to satisfy the law of conservation of mass. Products, reactants, products. Don't remember the thing I just said. This is the reactants. These are the products. We balance it across the yield sign. The things on the left side, the reactants, have to be the same as the things on the right side, the products, when we add them up. There are 5 types. I think your book lists 5. Some books list 5, some books list 4. There are 5 types of chemical reactions. So let's put the types down here. And then we're just going to name them and tell a little bit about them, and then we'll do them in the lab as a demonstration. So the types are, let's do the types, and then let's do the general form. The general or the generic form. Synthesis. You got what you need?
No, I mean
Another pre-filled one?
absolutely none of them.
What?
One of them said, I don't know, I would rather not at this time. And the rest,
Cool. Well, we,
I must do, but I have one
yeah.
left.
Okay. Just use the one for the rather not. Yeah. Okay. So the generic form for synthesis is A plus B yields AB. That is, something, doesn't really matter what, plus some other thing yields those 2 things stuck together. An example of this would be, let me find a place to write. H2 plus O2 yields H2O. One thing, H2, plus another thing, O2, yields H2O. And by one thing I mean not that there's only one atom, I mean that there's one type of atom. So it could be H2, it could be H3, it doesn't really matter. Well, I mean, in this case, it has to be that. Let's balance that real quick. Is this balanced? How many hydrogens on this side? 2. On this side?
2.
Oxygens?
2.
On this side? 1. So that's not going to work. So what can I do? Can I just put a 2 here? No! That makes it a completely different thing. You cannot do that. What can you do? We can only change the, so tell me the rest of the sentence. No, we can only change the, no, we can only change the coefficients.
Change the coefficient to 1 on the
Well, it already is 1. If there's no coefficient, it already is 1. Just like x is 1x. Let's work on the oxygens first. How many do I have on this side? 2. On this side? 1. So what do I need to do to get it to be 2? I can't add. I can only multiply. Of what? 2. Okay, so now I've got 4 H's and 2 O's. So the O's are happy. But is there something I can multiply the H's by to make them 2? Yeah, now it is balanced. 4 H's, 2 O's, 2 O's. That's a synthesis reaction. The next kind is a decomposition, which is the opposite of a synthesis. AB yields A plus B. So where this thing was 2 things coming together to form a new thing, this one is one thing falling apart to form 2 other things that it's made out of. Let's do an example of that. I'm going to use H2O2 now. H2O2 yields H2O plus O2. That's one we'll do in the lab if there's time. 2. So H's?
2.
O's?
2.
H's?
2.
O's?
1.
All together.
3.
3. Well, if I double this O, that'll make it 4 altogether. That means I can double this one. So now we've got 4 H's, 4 H's, 4 O's, 2 plus 2 is 4 O's. That's balanced. Okay. Next kind of reaction is single displacement. Single displacement. And this one is let's put it like this. X plus, no, let's do it. AX plus B yields BX plus A. They've switched. The B that was alone is now with the X, and the A is off on its own. Successful? Just hold on to him, okay? Okay, yeah, get back. Yeah, we are, because we got Kyla's grandparents. An example of a single displacement. Well, this one's a single displacement. Look, this is the A, this is the X, and this is the B, and now the X is with the B instead. So we've got HCl plus Zn yields ZnCl2 plus H2, and we've already balanced that one. Double displacement. This one is swing your partner round and round. AX plus BY yields AY plus BX. They just switch their partners. This is just like when you're a freshman, and Tom is dating Sally and okay, I have to remember these names, so give me a second. Tom is dating Sally, and Bert is dating Linda, and then Tom is dating Linda, and Bert is dating Sally. You know, like they just, you know this. I can see the wicked gleam in your eye. You know what I mean, though, right? They just switch. And since you're a freshman and dating means nothing to you, you might as well just switch. Double displacement. Let's get an example of that. Let's try, let me think of one real quick off the top of my head. Lead nitrate. I'm not going to have enough room for this. I'll erase 1787 in mass, and then I will. Let me switch to my other color that I was using. Yes?
This guy was wondering if we could take, because his well is like a whole mile away from his house, we could just take it out of like his house.
Yeah, that's how we have to do it. Let's do lead nitrate, PbNO3, lead 1 nitrate, plus Ki yields KNO3 plus PbI. Let's do it like this. It's actually supposed to be lead 2 nitrate. There we go. Sorry, that's a little bit messy. But PbNO3 2 plus Ki yields KNO3 plus PbI2. That one's a double displacement. So the lead was with the nitrate, and the potassium was with the iodide, and then they switched. Now the potassium is with the nitrate, and the lead is with the iodide. Yeah? Balanced? Here's a trick about balancing. If you have a polyatomic ion, you recognize nitrate from your last chapter as a polyatomic ion, yeah? You can treat that, as long as it's the same on both sides, you can treat that as if it's an element. You don't have to balance the nitrates, or the nitrogens and the oxygen. You can just balance the nitrate as itself. So leads, on this side, lead, 1. This side, that's fine. Nitrates? No, no, 2. There are 2 nitrates. The 3 is part of nitrate. This whole thing is one little guy. There are 2 of them. On this side, 1. Well, we can fix that right away, can't we? There we go. On this side, potassium? Potassium? No. 2. It's the K. 2. And then iodine on this side? And on this side? Let's just put a 2 there. There we go, balanced. That's a double displacement. And then lastly, we have combustion, which this is the one that sometimes people include and sometimes they don't. But it's always something plus oxygen yields that thing oxide. It really depends. There are a couple different configurations of this. For instance, if we have wood, cellulose, C6H12O6 plus oxygen yields CO2 plus H2O, that's a combustion reaction. You know what combustion means. It's fire. Is there a problem, Gunnar? It's a fire. Combustion is a fire. Something combined with oxygen releasing heat and energy. I'm not going to give you this general form is not even quite right. It would vary depending on the thing. And this one's kind of like, I'm going to put the approximately sign. We sometimes consider that a separate type, but it's also always, you'll recognize this is still a synthesis reaction. It's also always one of the other ones too. This was pretty quick and dirty. Do you have questions about this? The main thing we're doing is balancing chemical equations, which we have several examples of, and then you'll have to be able to identify the type, too, for the ones that you balance. Do you have questions about any of this? You need to have known your vocab. Everything that we would have talked about from lesson 4, which we didn't talk about, is vocab. So you need to know your vocab. If you work on your chapter review and your worksheet, you'll be fine. Do you have questions? I wanted to save some time for us to go in the lab. Do you have questions about this? Hopefully my microphone was on this whole time.